Alright, so here we go. Here's a couple more circular motion style problems. One of these, this car on a circular roadway, we looked at that in class, so I want to take another look at that because it's just so common. You're going to do this on the way home today. So let's take a look at it. So here is your car, and it says that the coefficient of static friction between your tires and the road is 0.4. How fast can you take an unbanked curve that has a radius of 50 meters? That's the first thing we want to look at. Okay. So if that is the case, let's think about this. Let's think about what forces are acting on the car here. What's the centripetal force? What's going on? Well, as you probably guessed, you are going in a circular path where the radiuses are. That's what's happening, right? I'm going to use red. That's a little brighter. So for this particular car, what is pulling it in a circle? Well, that's the question we have to ask ourselves. If we were to draw a free body diagram here of this car, I'll put a little dot back here. There's a lot of forces acting, right? Earth is there, so it's pulling down with a gravity, mg. There's a normal force from the surface of the road. In fact, you could pretty easily convince yourself that these are equal, that the force up equals the force down. But there is also a force that has to be pulling this thing towards the center of this circle, and that force is actually friction. If I were to draw it on this overhead view, I would draw it something like this, the force of friction. It's pulling you into the circle. It's the string that is attached to the rock. So that is our centripetal force. So, okay, knowing that, what can we do now? Well, we've got some numbers here. Let's play around with this idea. We know that the frictional force, hey, you weren't supposed to do that. We know that the frictional force here is our centripetal force, so we can also write that as mv squared over r. Okay, that sounds good, but what do we do with this? Well, remember, we know some things about friction. We know that it is equal to the coefficient, in this case, of static friction times the normal force. Alright, so it's static friction because your tires aren't skidding. We're dealing with a static friction. And that's going to equal, okay, mv squared over r. Okay, what next? Well, we also know something about your normal force. I was trying to convince you up here that the normal force is equal to the weight. So we can make another substitution here that can help us out. Mu sub s mg. Let's make the normal force equal to mg, and now we have this equation. And that's kind of handy because look at this. The mass goes away. Isn't that interesting? Now what can we do? Well, we're asked about the maximum velocity, that how fast can we take this car on this road before it just kind of slides out of control. Well, that's dependent on friction, right? How strong friction is. And it turns out that V max equals the square root, if I solve this equation for V, square root of R mu sub s g, which totally makes sense. Okay, it depends on how big the circle is. It depends on how strong friction is, and it depends on what planet you're on. What is gravity doing? Because gravity matters. And in this situation, we can write those numbers out. That's going to be the square root of 50 times 0.4 in this situation on dry pavement times 9.8. And that works out to be about 14 meters per second. That's about 31 miles per hour. Okay, any faster than that, and you're going to skid off that curve. And you'll see they'll put up special little warning signs about, like, hey, maximum speed such and such on this turn. It's because they've done some calculations. Usually they actually don't tell you the maximum speed you can sustain. They're probably telling you maybe half of that maximum speed because they don't want you to push it. They know people are going to always go faster than whatever that little sign says. So, but this is how they figured that stuff out. Now there's a second question here. It says, okay, now the road becomes icy like it was this morning, and your coefficient of friction is 0.17, so much less than this 0.4. Now how fast can you take the curve? So now if I do V ice, the only thing that's changed in this equation, it's same radius of the circle, but now I've got 0.17 as my coefficient of friction. Gravity's the same, everything else is the same. What do I get? 9.12 meters per second, or approximately 20 miles an hour. So significantly less, 2/3 the speed that I was originally was able to go with when it was dry. So it makes a big difference. If there's a little bit of ice or a little bit of water, your car just simply cannot behave the same way. So drive safe, folks. Okay, This last problem is a particular favorite of mine because I am a science fiction junkie. I love science fiction. I love it when it's good science fiction. I love it when it's bad because then I can make fun of it. I love it when the physics is good. I love it when the physics is bad. I just love it. And one of the staples of science fiction is the rotating space station. This has been going on for a while. Why do they always have something out in outer space and it's spinning? Well, if you think back to our demonstration of the water in the cup that we were spinning, it might make some sense as to why they want a spinning space station. And that is to simulate artificial gravity. It doesn't have to be water that's stuck in that bottom of that cup. It could be people. And this was done in the movies, in a classic 2001 A Space Odyssey, that Stanley Kubrick film. They had the space station called Space Station 5, and it was this guy right here, and he would rotate, and as he would rotate, the people inside the rings here could do things. This is actually a scene where this guy here is going for a jog. There's a famous scene in the movie, and as he's just he's jogging, and he's jogging in upside down, as to, you know, it seems that way when the camera is panning around. So it's a really kind of a brilliant scene. It's worth checking out if you can find it on YouTube. And more recently, the movie Elysium had the same idea, except there was much bigger. They had this massive ring world that was spinning enough and generating enough gravity that, you know what, there was like a whole atmosphere. There was breathable air down here and things like that. But even though you notice in the movie these ships just kind of fly in, but that's because there is atmosphere, a bubble of atmosphere that's trapped, just like the bubble of water was trapped at the bottom of the cup. So that's pretty cool. And maybe we'll talk about that whole exoskeleton thing later on. But what can we do with what we know? And talking about this Space Station 5 and 2001 A Space Odyssey, well, let's take a look at this. It turns out that in the movie, I don't have my... okay, there it is. I lost my little text here as to what the problem was. Okay, here's the problem. In the movie, Space Station 5, which is in 2001 A Space Odyssey, appears to rotate once every 61 seconds. Okay, and the question is, what radius, how big must this thing be in order to simulate 1 g of gravity? Meaning the same kind of gravity that you experience on Earth, a centripetal acceleration that equals 1 g. What do you got to do? Well, okay, let's think about this. As you know, centripetal acceleration is v squared over r. We also, I'm going to go ahead and do it here, but you don't necessarily have to write it this way. But you can make a little substitution here where v is 2 pi r. You don't have to prove this every time. Over t, the orbital period, squared all over r, and that actually reduces to a different formula for centripetal acceleration that you can use, which is 4 pi squared r over t squared, right? And I think that's the one we want, because it says we're going to rotate this thing once every 61 seconds. That is what orbital period is. That's what the rotational period is, t. The amount of time it takes to rotate once. So they gave it to us, so let's use it. So basically, we've got the situation where this centripetal acceleration has to equal g. That's what we're looking at. That's what the question was asking. And we're designing this thing. How big does it need to be? So we got to solve for this guy r. And it turns out if you just do some quick algebra here, you can solve for r. R is equal to t squared g over 4 pi squared. See if you can convince yourself of that, right? Just kind of rearranging some things, bringing all this stuff over to the other side. And now we can plug in some numbers here. So we got 61 squared. Well, g is 9.8, and then 4 pi squared is just constants. And when you run that through your calculator, you're going to find that's 923 meters. And that's pretty darn big. That's really darn big. And in fact, according to the 2001 Wikipedia, there's a huge Wikipedia article on this thing, the space station was said to have had a diameter, which is 2 times the radius, of 300 meters. So wait a minute, that doesn't work. That doesn't jive with what we got. But you know what I did? I read a little bit further in that entry on Wikipedia, and they also said that the gravity, it wasn't spinning so that it can have a gravity equal to the Earth. They didn't want that apparently they wanted the acceleration due to gravity on the moon. So that's apparently, this thing was spinning, but it wasn't spinning fast enough to simulate the Earth. Where did we go? Right here. It wasn't spinning fast enough to simulate the Earth. It was spinning fast enough to simulate the moon, and the moon has less gravity. In fact, the moon's acceleration due to gravity is equal to 1/6, roughly, that of Earth. So that changes things. We were looking for making this thing look like the Earth, but they just want to have, although it doesn't look like that in the movie, they look like they're walking around just fine. They supposedly just has the acceleration due to that have done to the moon. So let's take a look at that. So if we run this, we look at this equation again, r equals t squared. I'm going to use g on the moon now, 4 pi squared. Well, effectively, if this is 1/6 little g on the Earth, that just means I got to multiply everything by 1/6. That means that r is actually a sixth of this, which is 153.9 meters, which, if you double that, that's pretty darn close to 300 meters. Nice job, Stanley Kubrick. You did your physics. You did your math. And so apparently, they were pretty spot on in that movie. There's some neat physics in that movie. You should check it out. It's a little dated. It's a little weird. This one was cool. I like that a lot. But anyway, hopefully some of this helped in terms of seeing all the different kind of applications we can use circular motion physics for.